Ma prego. Switch into English.
Interpret, you study things that we observe from the space. So this is from the research lab to the space. However, I will start with this is my collaborators here from the UFRJ University, Victor, Simone, and Camila. And today we'll talk about measurements done at the Catholic University of Rio, PUC-Rio, and also made with Emil and Rodrigo while he was there. Sérgio Melo is from the Federal of Viçosa, another state in Brazil, from Minas Gerais, and Rafael from Amapá, Federal University there. So this is the lab. Before the research lab, I will talk to you about something that we did during the last 2 years at the Federal University. We teach per semester to about 1,000 students from engineering and physics. And we have introduced an experiment on the first course, Laboratório de Física, Lab Physics 1, first semester. But we introduced something different here to introduce to them the collisions with a target that has structure. So this is our molecule. And I will show you first how can I get there? This is different. Escape. I will show you the actual experiment first. Where is it? Here. Okay, so this is an air track. To minimize friction. And what they do is that, well, they set up this 2 blocks here that will slide with a spring here, a light spring, stainless steel light spring. And then you have the projectile here, and they film with the cell phone and analyze with this tracker program, free software, and then interpret what's going on. So the main question for them will be if this is an elastic or inelastic collision. So it goes like this. So after the collision, the 2 blocks go on, and we have at this moment, analyzing the data, we have plots for, can do several of them, but here for position as a function of time, velocity, and acceleration. So I will switch to the presentation again. It's easier here. Okay. And what we ask them is this. Is it an elastic or inelastic collision? So in all of the plots here, of course, you have a signature of momentum, total momentum conservation. You have a straight line here with a constant slope, a constant here at the velocity of center of mass, and acceleration 0. If you look at the center of mass. However, you can see here the 3 blocks. These 2, if you follow them individually, they have the oscillations here. They are pretty clear. And when they see this, if you ask if it's elastic or inelastic, they say, oh, it's elastic, because they are not measured, but they see the spring here. Here we have rubber bands. And they say, oh, this must be, you must conserve the total energy. And they said that. It's not wrong. I mean, the answer here depends on how you see it. But the way we see when we do research is different. So what is an inelastic collision for us? It's a collision where you excite some internal degree of freedom here. And with the same data, when they plot the global center of mass, the center of mass of only these two and the projectile here, they see something that is inelastic collision. So the projectile stops, all the energy is gone somewhere else, and the target, the center of mass or the target has part of the energy, but not all of them. If you analyze conservation of energy here, you see that about 42% of the energy is lost. It's not really lost in this experiment. We cannot do that in general, in a general collision experiment, but here we can look also at the individual parts here. And then if you model this as a harmonic oscillator, it's enough to get this kinetic and potential energy in the target. And you have here the center of mass energy. If you add them all, it's almost, you have the conservation here. But it's still, this thing here is because of the rubber bands. Huh? During the collision, you have energy there also. So why I'm talking about this here? Because here you see that there is a frequency, a proper frequency of the target. So if I change the velocity of the projectile, or if I change the mass of the projectile, what will change here? The amplitude of the movement, the amount of energy that goes into the center of mass of the target, but not the frequency. The frequency is a property of the oscillator, this thing here. Right? So imagine if I have here a white light, many components of different frequencies. So this thing here, the molecule, the actual molecule that I'm going to study in the lab and in the space also, they also have the natural frequency. So if you come with different frequencies here, and one of them matches this natural frequency here, it probably, or it has a larger chance than for other frequencies to be absorbed here. So you see red is here, it's not here. It was absorbed. So this is observation number one. Another one here, another thing that happens here, and also many times when I'm analyzing more complex molecules, is that not always you have this harmonic potential. Sometimes they are anharmonic. In this case, within the target, we have this stainless steel spring, and the movement is almost harmonic. So we have this linear force here, and of course the square potential, but not for the rubber bands. If you look at the rubber bands here, the force is far from just linear. Well, I will not discuss the details here, but I'm showing this to see that here you will have this anharmonic effect. Potential will be anharmonic. And this happens with molecules also. So if you have this harmonic approximation, you have the levels here, the energy levels equally spaced. Then it doesn't matter, for example, with temperature. If you have a distribution here, it doesn't matter much for what you are measuring, because this transition here has the same frequency here. But then if the anharmonicity is important, these will be different, the spaces here. And different transitions may occur here. So if you have a measurement as a function of temperature, for example, you have, if you begin to increase temperature, the frequency where you will observe the absorptions will change. You know? This is an example here. So one real example is this one. This is potential energy curves for both O2 and O2 minus. These are calculated by these guys here. And you see here, oh, the lines are not very clear, unfortunately. But on the zoom here, they are harmonic. Of course, they are not harmonic all the time because they would go to infinite. So they start to become closer until the dissociation is allowed here. But if the experiment is performed within this region here, you see here, these are actual numbers, calculated numbers. You cannot see any anharmonicity here. So those for O2 and O2 minus. Then you can, if you have this levels here, the distributional levels, it will impact for example, the cross sections for electron scattering. This is total electron scattering in O2, calculated by the same guys. This is inverted, so this is basically the electron energy here, the projectile, and you see that you have intermediate states, metastable ones. The electron will be there at the target for some time, and then this intermediate state can be different ones, and then the final here. So these are calculations. We have also here in this plot, together with data that I will explain to you that we are measuring here. These are for electrons. This plot shows cross sections as a function of velocity, both for electrons. Those levels are calculated in the previous slide are here, and you have cross sections here for total electron scattering. And also I put here this is also illustrate the kind of work that I'm doing here with Guilherme. We submitted this recently while I was here.
Make sure I understand, going back to the previous one. And in photos, the prime common factors sort of tell you how the shapes change. So for electrons, is it still the same? Low energy electrons? Or I am getting.
These are low energy electrons for sure. Yeah.
And then I understand you get this different shape or because the final state is different, so the potential moves and the overlap integrals.
Yeah, you have two things. Well, you have the non-resonant scattering. You have that component. It's not here. But it can also, I represented here for ions, but it happens for electrons also. If you come with an electron here, it can be only scattered there, but it can be, it's a temporary capture, let's say, a resonant temporary capture. It can be here for some time. Of course, there is no trajectory like this, but it will be here for some time. There is a time that you can measure for that. It will be related to that width on the last plot. Oh, here also, you can see here. And then it goes away. So then you leave the molecule here in the ground state or the first excited, the second excited. But there is also the intermediate state. And that you need another quantum number to say, well, what was the intermediate? Of course, you only measure this resonance here, the total. No? I cannot see. This will be the sum of all of those channels for the electrons. Then for the ions, what we see, this is those are equivelocity O2 minus ions on the same target. Then the thing is that for the ions, the binding energy is so low that they are quasi-free, let's say. So they behave similarly to the electrons. Of course, this is an experiment that's not a place to learn about the spectroscopy. It's a place to use it. So we are affected here by these levels, but they will be all mixed here because you have this, you need a convolution of the velocity of electrons with the distribution on the projectile. It's loosely bound, but it's still bound. So there is a momentum distribution there. Okay, so ions are bad for the spectroscopy, electrons are better, but the best ones are the photons, huh? As I have shown before. So let's go there. So this is, you see, that molecule was very simple. It was the atomic molecule. Huh? Now, if we go to a polyatomic molecule, you have more than one mode of vibration, the normal mode. You have here actually 5. This one is represented here. It's 2 of them going up, down. The other ones, but you see, not all of them will show up because it depends on the technique used. If you use the absorption here, you need modes here that have what do you call it? The momentum here, the dipole momentum during the collision. If you associate a charge here with the carbon ions and another one with the hydrogen, when this goes down and this go up, you have imbalance. There is a momentum there, will change with time, but you have it. Same thing for this one, the stretch asymmetric, but not for the other ones. For this, it's perfectly symmetric. So this technique will not appear unless there is something in the environment, another molecule, a solid, something that breaks the symmetry. And then these forbidden modes may appear. Like an amorphous solid, you can have a contribution. Okay. So here, going back to that same example before, I don't have only one, but I have several. These two are active here. So I'm representing here something like this. For this mode, the red will disappear here. For this mode, it's different. So I made the orange one disappear. So we will have peaks, we will have different frequencies corresponding to different normal modes of the molecule. So these are diatomic, polyatomic molecules. And things can be more complicated. Let's go for the solid. So this is a crystal, perfect crystal, an example, alpha quartz, and it has periodic boundary conditions here. So you only need, when you model this, for example, you're making calculations, you only need to make it with a small portion, and then you know what's happening with the solid. Here you have phonos, but again, you have several modes. And for this solid, in each side of the lattice, you have one atom. This is different from what we will look on the space. We'll have molecules. But let's see first this one. So here you see, if I plotted here this experimental data, also imaginary part of the permittivity, and you see those different frequencies corresponding to different modes. These are calculated by nested functional theory. Here, actually, we have two of the silicon atoms. You can only see one here because they are oscillating together. The red ones are oxygen. And a small difference, for example, in this and this, the only difference is that the phase between the vibrations is the same. They are both unsymmetric, but here you have this in the neighbor tetrad. They are in phase here and out of phase here. It's enough to get this different frequencies here. So this has the translation symmetry. If you
Can I do an ignorant question? A gas phase, okay? The gas phase, this symmetry, Robert dipole active, that's clear for me.
Same thing.
Same thing.
Same thing. Yeah, you have modes that they don't appear here. You have others that do. Same thing, except that you have phonos here. Now, if you add disorder, from the point of view of the calculation, that's terrible, because you lose the translational symmetry here. Then the calculation will be much worse, because then I need to make a big cell and introduce the disorder, and something that will have to change and test. So this is much more difficult to model than this. If you add defects, even more difficult. So I plotted here the real part of the permittivity. You see here for these are all experimental. If you see here for the alpha quartz, the crystalline one, you have this very well-defined peaks here, here, and here. But if you add the disorder here, you have something similar, but you can see here that some kind of convolution with the crystalline one works this sometimes here. If you add defects, it's more difficult. This green one here. Okay, so this is still not a molecular solid. Now, this is closer to what we want to study in the space. So at the two examples here. Now I will deal with in detail with this one, But you see here, they have different symmetry groups. They have different phases. I am only representing one of them. But here at each site of the crystalline points here, you have a molecule. So it will have the spectra will have this characteristics of the solid, the phonons, etc., but also of the molecular levels. They will be combined there. No? We have to interpret something that will show both things here. And each one of them will have a different symmetry, and each one of them, of the phases also. This is the one that we are going to study in the next slides. Oh, it's wrong. It's 284. No, it's 222. But it's settling. Okay. So now in space. So what we want to study with these things that we measure in the lab. This is the James Webb Space Telescope before it went up. It was launched not long ago. It observes things in this 0.6 to 28.5 micrometers range, here in centimeters to -1. However, it doesn't use only one spectrometer. So when you go and look the data, they publish, it will not cover the whole range. So I will show you why this is important later. But this image is enough to see that we look, it's not better than this, but it's different. You look at different characteristics of what you are looking if you use infrared or another range of the electromagnetic spectrum. And this is good for situations in which we want to get information from the molecular vibrations. The first link here. So a few recent observations. This is from 24. They observed dwarf planets. This is Sant'Anna, one of them. This is our solar system. This is they call it trans-Neptunian. This is the approximate orbit. And they observe, so this ray, you see, it doesn't cover all the modes of the molecule, but it covers a lot. We get a lot of information here. This is one for each of these objects. And you can see here, they put this, this is not mine. They put these question marks here. So this is the question, if this is C2A2 or not. So when we studied on Earth, we are trying to know what's happening here with this. And also here, this one, they think they don't. So this is 24. This is something that we have to sort here. Another one. This is also 24. And this is about Cairo, another kind of object. And they have their data. And there's something here that they want to know. They are not sure, but they think it's related also to C2H2, another with more details here. So what they do here, they compare the spectra. This is a experimental spectra from one guy that I'll show you that has a really impressive work on the area for C2H2. And then they want to say, they think that this is the responsible for this structure here. It's unexpected because it should not be there. The hypothesis that all these guys are making is that this is coming from CH4 irradiated. And then it's changing and producing some C2H2. You see this irradiation process is basically, it brings a lot of defects and disorder to the system. So this assumption that they are created this way it tells you that it's reasonable to expect a lot of disorder in this system. Oh, okay. This is from the guy that I was telling about. This is an expert. He has in his site all his data. He wants people to go there and think about the subject. Very positive attitude. And they published it here, 2014. They work with C2H2. And they see here, playing with temperature, two different phases. When they grow these ices at the lab, they measure the spectra here. And you see, if they did several tests, but on this one, they grow it here. And then when they hit, it doesn't change much. And then you have this. So the hypothesis that he made here with some, he says, oh, maybe is that this is crystalline. So this is amorphous, and then it turns to something crystalline here. Okay, so it's there on the title, no? But we suspect that that's maybe not true. Okay, another one here, 24 also. Okay, these guys, these are theoreticians. What they did here, they they simulated a target of CH4. And in their simulations, they have 7 ions, H plus protons, with this energy here. Total energy is this one here. And in their simulation, they see what they produce, what they form. They count the molecules there. They have a list here. C2H2 is there, it's here, and a lot of other stuff. But you see, this is also amorphous. So what they are saying here, it doesn't have any assumption about crystalline structure. It's compatible with the idea of the ion beam, being the disorder there. Okay, so how do we measure this at the lab? This is at the Catholic University of Rio. Doesn't say much. Let's see a diagram here. So what do? We have the chamber in vacuum, the ion beam. Oh, actually, this, why do we need the accelerators? You don't need it if you don't want to introduce the disorder, but that was the case here. So you need the gas initially, a cryostat. You are going to have a flow here of the gas, and you will grow the film with some rate. You control that, and you get a sample here, a nice film with the thickness you want. At the same chamber, you have the tool to measure the infrared spectrum here. So this thing here goes from here, this direction. The gas goes there, and you start to grow the sample here. Okay, these are the dimensions typical of the film, the ones that we use it for the data. I will show you in a minute. And okay, this is a typical spectrum. This is not for, I took another one here. This is not for C2H2. This is for CH4. They measured that also there a few years ago. And that's what you have from your experiment. You have this notation here, it changes from one molecule to the other one. So you have to study a little bit the molecule to see if this is a stretching or symmetrical. But then you have some contaminations here. You have also here some modes. You measure them here. They don't correspond to one or the other mode, but a combination of them. So somehow the molecule oscillates in a combined mode, and it's resonant with the light that is coming in. So you also have this kind of thing here.
Marcelo, can you safely assume that you're not melting the ice? Very silly question, but maybe
no,
with that second.
No,
okay,
no, it's not a silly question. But what melting?
Or changing the combination. What you want to measure.
With ion beam, you mean?
I mean, you have your eyes pristine.
Then
you send your infrared to your spectroscopy, but that will deposit energy and make change.
No, well,
Just speculate. Or it's nanosecond pulses, fast pulses that we can.
Well, the ion beams change a lot. The light itself No, because then it would go on with time. You don't see when you are measuring one thing, you don't see it changing with time. You can measure the hours and it will be the same. It's not the same thing with the ion beams. If you put the ion beam and monitor, no, you don't melt it, but well, it depends on what you call melt. If you start with a crystalline, it will become amorphous. So is this melting? No, but somehow it is. It has the idea of being disordered like a liquid, but it's not liquid.
I was thinking resonant, positing and resonant. You don't have too much places to send the energy away. Through a vacuum, I guess. That has to go to kinetic energy.
Yeah, well, yeah.
Speculate.
No, it's on a substrate. It is deposited on a substrate thick that is transparent, but it's not self-supported. It's there. Yeah, it can. And also you are on the cryostat. So the cryostat is all the time removing to keep the.
Yeah.
So unless it's a really strong pulse, and then you melt silicon if you do that. Huh?
Okay.
The light is under control here.
For this sum, it means you have one more frequency, the sum of two other modes.
Yes, they are in first order. The frequency is just the sum of the other two. Then if you go to an harmonic effect, it will be a little bit different, but not much. It's basically the sum. And the molecules, it's vibrating in a configuration that is not of the mode 1. It's not of the 2, not the 4. It's doing something there. It absorbed only one photon.
Or it's not one mode that is combined.
It's not a new mode. Well, it is a nonlinear. Good question. I'm not sure if I can give a good answer for you. It absorbs one photon. It vibrates. If you make an animation of this, it will be something similar to the other two. At the same time, it's like a superposition of the other two. Because that's true also with the classical. If you make that first experiment there, actually I did that, not with a diatomic molecule. I put 3 blocks with two springs, and then it doesn't oscillate in one mode. It oscillates in, we think in one mode, but it's in a combination of the modes. Here's the same thing. It's in a combination of the two modes. They are not independent. And the signature of this is not visual. It's the frequency. But it would be interesting to model this and to see how geometrically how it oscillates. But it's very common. It's not something of this target. It's something very, very common. It happens also with C2H2. You'll see in a minute. You see now. So this is from the group of Enio also, 2020. And this is a typical spectrum that they got there for C2H2. Now, so you have these two modes here. They are the active ones, the asymmetric ones that I told you before. A little bit of contamination here, and also this other one that is a combination of 5 and 4. 4 is actually inactive, but some part of the molecule is vibrating here in a way that it has the dipole momentum. Okay, and then let me show first the results. I will concentrate now on the discussion of this one here, this bending mode, although the other one is important, more than I thought at that time. We started the measurements. And they changed the projectile, the energy here, and also the deposition rate. Several situations here to check see, to study how the disorder is changing the system here. So let's discuss this one here. These four, they correspond to different projectiles here. And each curve of this is for one thickness. No? They are growing here. And they change, you have the two phases here. So I showed before the Woodson data, showing these two different phases changing with temperature. Here you have something with the fluence, actually with the fluence here. And you can see also the two of them. But look something here that's suggesting the amorphous instead of crystalline interpretation. The zero here, the zero fluence, zero is zero for any projectile. It's before the radiation. So they should be the same in principle, but they are not. If you look at the first, you have this structure more clear here, less here. This is wider, the other one like this. So what's the difference between them? It's the deposition rate. So at least they cannot be all crystalline. They should look the same here. So that is maybe not for this one, but at least for the other ones here at the beginning, you have something different from a pure crystalline sample. We think that this is not crystalline also, but this is an indication, another one, for disordered phase there. So I will show you other data on this system, changing with the annealing, and also combination of this with the DFT calculations to interpret the data. So the same thing here, this was done also the same chamber. Now this is more recent, 2024, but it's also CH2 grown the same way, infrared here. And I will focus on the discussion of this Benny modes. This one is only, it's CH2 on a transparent support here for infrared. The ice is solid, that's for sure. No, it doesn't have any water here. Although in space, in several situations, these materials, they are together with water. This is an important problem. And in the lab, there are several works in which we put the one material and also water together in a controlled way, because it's important for it happens in space. And then you have other situations. This one, no, this one is only C2H2, no water. If water would be a contamination here, but we didn't see it there. Okay, and then you see here, we have grown here at low temperature. Then you have this phase that everybody agrees that is amorphous. And then if you hit the same behavior, you hit it, you go to this one. If you go down, it stays there. So you have these two phases here. We agree that there are two phases. But you see here, well, another observation here. If you now irradiate the sample, so B would be the more, the one with less disorder. We agree on that also. Crystalline or amorphous, but it has less disorder. So if you irradiate, it goes to this one here. So we see this also. It's another indication here that this has more disorder than this one here. So let's see how can we use our first. Let me show other data for that. This is all. These are all films, but that's not the only one to produce this. The only way to produce this ice. So these guys here, they use an expansion to produce in aerosol. They expand the material, and they have, in this case, you see, I'm comparing here the data from the NIST website. For vapor, so this is gas phase. You see also the rotational levels here. This is the center. And then this is the Woodson. They are also films. You have the two phases here and sometimes something here in between. And this in the aerosols, they are more to the right. So this is an indication that there is still more order, another phase here. Then when we made the calculations here, the DFT calculations for dimers. So here we put two molecules together, and for the crystals. And they also show up in different positions here, about the same difference here. So we think that here, the Preston data, they have the small crystals there, but the crystals, but this is more close to the dimers. So what we try to do is the following: is to model this amorphous phase, or both amorphous phase, because we think there are two amorphous phases, using the calculations here for the monomer, it's right here, and for the dimer in different configurations. So if you put these two molecules far apart, they will become the monomer. It will be the same thing as this. But in the equilibrium situation, this is the result from the actual calculations. These positions are real, let's say, they are in scale compared to the distance here to the atoms. You have here, you break the symmetry, you have 4 different situations here. I think it's easier to see it here with the animations. You see this is going up here, out of phase with this one energy, observe it. They are in phase here, the hydrogens oscillating, another one. These are in plane here. This is almost stopped, and this one like this, and another one here also in plane. So they give rise to this thing here. Of course, the amorphous solid will be much more complicated than this, but that's something that people have done. To model this is, let's think about a series of the monomer, dimer, trimer, etc. And these are the first terms. Right? The trimer we calculate also, it could be small, it's something like here. So what we try to do now is to use this calculation here to describe both phases that we have measured. So we put them in the same scale here, that is a scaling factor here. But you see here, the width is compatible. In the shape here, this phase, it's basically this one. So what we think is that in this situation, we would have basically the more dimer configurations, a little bit of more monomers. And in the other situation, we'll have more monomers, less dimers. But not in any, they would appear here, not in any fraction. They would, there are two, what we think is there are two configurations that are stable and produce these two phases. This is well known for water. Water has a very complicated phase diagram, but it's well established that they have these two amorphous phases here. LDA is low density amorphous, and this is high density amorphous. And they appear one or the other combination, but they are two different phases here. We don't have crystalline measurements here, crystallography measurements. That would be nice. We don't have the tools to make it. We would have to test, but what we are suggesting is that we have actually both two amorphous phases here, both this and this one here. Okay. This thing here is, I saw it yesterday. So it's from last month. I was preparing the talk and I found it October 1st. So it's very recent. And it's relevant here. So let's see what's happening here. This is a different object here. They observe it also. They think they are observing C2H2. But they model this, and what they think, they also suppose here that you have the CH4, methane, ice, basically. They think they have water there also. But in the surface, they think that the radiation is building there, this layer that is not only C2H2, but C2H2 with C2H6. And then they made the fits there, and then they said that it describes much better what they are observing. So it's a very recent proposal here. So one thing that we could do now, some ideas that this gives, is to try the dimer thing with different molecules here and see how this is changing, how this changes. It will have still the basic configuration of the vibration mode here of C2H2, but the neighbor is different. So it will be affected in a different way. And then running DFT for this, for example, we will have also how a spectrum of C2H6 changed by the presence of this one. So this is the kind of thing we can do here. And then try to simulate the amorphous, the configuration that they have here. This is something that we can do. Another possibility, if this is a solid, there are solids, molecular solids, with different molecules. They call it co-crystals. So this is another possibility. Even if it's solid, you can have the sites there, the lattice, and we have on one of them C2H6, C2H2, and this can repeat with periodic boundary conditions. This is also possible, although I think that that's not what's happening here because of the arguments I gave you, showing that this is probably a amorphous phase. This would be also, and they are being created by irradiation in this model. It will be weird if they are crystalline, at least if there is not a component of the amorphous phase. I think so. But you can see it's a discussion going on. And in conclusion, so about the signatures that we have in space in our work on the lab, we think we have actually two amorphous phases. There is a crystalline one also. We see that in the present data for the aerosols. But in these films that we have been studying, we think that they are both amorphous phases. There is one other thing here. All our analysis was done for the Ni5 band. Unfortunately, almost all this data that I have shown, they are for the Ni3. So nice to have the actual quantitative, something that works for one is the material. It works for the other one also. The whole modes come from the same molecule, but it would be nice to have this analysis for this other mode, the stretch and the asymmetric stretch. And this I have just discussed with you, this possibility. Maybe it is. We can do that. We can mix them in the lab with two different gases, make this in the lab, and we can also simulate this with EFT. Okay, then this is it. Thank you.
Any questions?
You mentioned simulations, so that where you say simulations, you have how many molecules are in the system that you try?
So all the simulations are for, well, when it's crystalline, you have periodic boundary conditions. So you enter there in the program with the group symmetry, the atoms, the position, that will optimize the positions, and then calculate the frequencies. Well, for the dimer, you only have two molecules in the space. So you have one and his neighbor. Or of course, we did that. You can put more. You can put the trimer and other molecules, larger molecules. And we did that. But they are kind of in the right position. But these two are enough. So we didn't want to complicate the model.
Mm-hmm.
But it's in the position where there is a tail. So it's reasonable. But in this case, here, you see, the trimer would be something like here. So it's consistent. And then the other ones will stack here. But this is two molecules, so two molecules.
I'm just thinking that perhaps we can do something here.
Any other question?
Thank you. At the beginning, when you showed this demonstration equipment with these pieces that move and may have inelastic conditions. Yeah.
We can,
Have you been able to do demonstrations of these resonant collisions where the projectile is oscillating and the target oscillates and then you have a resonant transfer?
yeah, well, the thing is that this is for the first semester students, freshmen. So this is already hard. But of course I did with the lunchtime. And with this, I put here one projectile and three here.
Yeah.
And then I made the Fourier spectrum of that. And then you see two peaks there. You see the two modes. Always the same. Maybe if you change the velocity, the mass of the projectile, they are the same frequencies. So that way you can have many variations here. But I cannot do this with the freshman.
Thank you.
Yeah, no, some of them you have like 1,000. So some of them are looking like this. But you have others that they want to go and do more difficult stuff. Yeah, we give them. We have lots of stuff.
My question, and it's Christoph is not around here, and he's the expert. But I think it's fascinating that they can see the spectra from these far, far away objects. But from the astrophysical standpoint, what do they want, or what do they learn from seeing that there's this ice or that ice from this hydrocarbon or PAH?
You see, for example, the processes of formation of these molecules. How from simple, this is an example, from simple molecules you get, I was talking about C2H2 because that's what I measured, but you can see in their list. When in the simulation here, they have a long list of molecules that they create. Here. So all this came from methane. And it will evolve, it will depend on is this an ion that is bringing this energy, it's a photon, how long does it take? And you have to model this, it's seconds, it's years.
Like the modern version of these operating experiments, right? Where they have atmospheres of discharges and so on.
Yeah.
Probably.
Synthesis.
Fascinating.
Well, if there is no more further questions, let's thank again Dr. Sant'Anna.
Thank you.